Hello and welcome everyone to season 4 of Contact's Produce Safety webinar series. This series, of course, is part of a larger industry outreach and risk mitigation project called Contact, or Scientific Challenges and Cost-Effective Management of Risks Associated with Implementation of Produce Safety Regulations. This project is supported by a specialty crops research initiative from the USDA National Institute of Food and Agriculture. Any opinions, findings, conclusions, or recommendations expressed in this presentation are those of the speakers and do not necessarily reflect the view of the U.S. Department of Agriculture. In this season, and we're very excited about season 4, we really want to focus on topics that have been in the news related to produce safety, so things that you all want to hear about related to flooding or climate change, ag water, post-harvest water. But we also really want to take a moment and focus on our research to reality and be able to share with you all of the Contact grant-related research. And so we will today, some of the research is affiliated with Contact. And then, of course, it always goes a little bit bigger. So we'll really try and tie in some of the research to what's going on and how can we practically use this in the field as well, all the way through the supply chain. Also, this is our last year of grant funding, and we've all really appreciated and loved working with you all. If you are a fan of the Contact webinar series, we would really love for you to let us know. You can reach out to myself, Laura Strawn, or our grant leader, Michelle Daniluk. We're actively seeking letters of support or just feedback to see if we should, in fact, continue the Contact Produce Safety webinar series into a season 5 or beyond. Is this something that's run its course, or is this something that you all really have loved and enjoyed? We hope you have, because it's definitely a labor of love. Who is Contact? It's a large grant comprised of several universities and government institutions. It's more than 50 faculty, staff, students, and volunteers, not to mention the support of our Produce Advisory Committee, or our PAC. For those of you in industry, if you're interested in this next iteration, wanting to get onto that Produce Advisory Council or have your voice heard, it's a very inclusive environment. Turn no one away, right? We know it takes a village. We know you're part of it. And we're very appreciative of each individual's support and ongoing efforts to make Contact a grant champion by all of you. This is the time. We will have a survey eval when you close out the webinar. So if there's anything that you would like to privately let us know about or anonymously, you can do that as well. Good, bad, and the ugly. We will take it all. And we always try and read and improve based on those comments. So let's get to the task at hand, right? Why are we here? We're here to talk about this comparative evaluation of commonly used agricultural water chemical treatments. We have two really fantastic extension specialists, researchers in the field, both full professors, but Dr. Channah Rock and Dr. Faith Critzer. I am going to let them introduce themselves, and we'll go ahead and let them share their screen and here's some really good research to reality when it comes to water treatment.
So, as Laura said, my name is Dr. Channah Rock. I'm a water quality specialist here at the University of Arizona. Speak a number of different times to this Contact platform about agriculture water and more specifically diving into subpart E. So I'll just kick us off and start off about a reminder about what's going on with agriculture water and why we're paying so much attention to that. As we all know and have seen with historical FDA environmental assessment reports and previous outreach reports, a lot of attention has been played on specifically agricultural water and their potential role as a source of pathogens in outbreak scenarios. As a reminder, this new revision for subpart E under the produce safety rule just came out, and it reframed what we saw historically really focused on agriculture water testing and now shifting into this new space and asking growers to conduct what's called an agriculture water assessment. So we talked about this a bit before about really what FDA is looking for industry to do is to evaluate hazards that potentially could impact agriculture water quality. There's a pretty big focus on adjacent land use and a risk assessment associated with those as well. Underneath that kind of umbrella of conducting an agriculture water assessment, there are a number of mitigations now that industry may be able to take to potentially mitigate the impact of the agriculture water quality on their production system. We've got those all listed here, but the one we're going to be highlighting, obviously, is agricultural water treatment. Again, as a reminder, some of the compliance dates for Subpart E, a lot of the folks that I specifically work with in Arizona and California fall into that larger category on business side. We looked at the effective date for Subpart E under July 5th of this year, and that compliance date coming in April of next year for those larger folks. And then an additional year and 9 months, or 2 years and 9 months after that for the additional folks. Again, as a reminder, that old rule really did focus on water quality and water quality assessment. And you can see on the left-hand side, we have those values related to agriculture water quality that we were looking at before, specifically focused on generic E. coli and looking at that profile of either creating a geometric mean or a statistical threshold value. And again, this final rule is looking at an agriculture water assessment. Why we're talking about this today is that reminder is really based on those exemptions. And so again, those exemptions might be using water from a public water system, obviously with a certificate of compliance. If that water quality meets those requirements through testing, in addition to a water assessment, or if you're treating in accordance to the rule. Now, we still these slides from FDA, just to let you guys read through them real quick. We do get lots of questions still related to testing as part of the assessment. And really, looking at Subpart E, they want to allow for flexibility to account for future science or potentially evolution of what we know to be appropriate mitigation. Still, test organisms, we're still talking to growers about the use of generic E. coli, and that's still a valid test, but potentially that might be other valid indicator organisms or other index organisms that growers could potentially use to assess their systems. Additionally, related to sample frequency and microbial criteria, we want to be able to have that flexibility. Looking back at what was originally published in 2015 and then allowing for science to evolve moving forward. Additionally, testing as part of that assessment is not required, but potentially farms could choose to use sampling under that framework and that microbial criteria that we saw in 2015. It is important to note, however, that if a farm was to choose to do sampling as part of their assessment, that test results are to be considered as part of the assessment and not as standalone. So a big part of what we've been working on under Contact Objective 1 is really trying to think through how growers would implement and become compliant with these new Subpart E requirements. And again, thinking through those mitigations and agriculture water treatment being one of them. Because industry and then those of us working in this space on behalf of industry were able to communicate about these potential issues related to agriculture water treatment, we worked with FDA and EPA to see the publication of a protocol. So basically a protocol for the registration of treatments for pre-harvest agriculture water. And that was done a bit ago, so July 2020. And really what that allowed for was for chemical companies to basically have something that they could go to produce data that says my chemical and this specific label is appropriate for agriculture water treatment, and more specifically included the use and the evaluation of human health pathogens. So more specifically in this protocol, FDA and EPA kind of came together to look at multi-strain cocktails of Shiga toxigenic producing E. coli as well as Salmonella. Originally, they also had Listeria. As part of that, after communications with FDA and EPA, we were able to get that Listeria requirement removed. And so moving forward, most folks who've been doing efficacy evaluations of water treatment options have been looking at Aztec and Salmonella as the primary drivers. So here's the website for that. This is the efficacy protocol for reduction of foodborne pathogens and bacteria in pre-harvest ag water. You guys can pull this up online, but this was the update in January for the removal of Listeria. So again, one of the big things for us and why we've been working on this so heavily as part of Contact and Objective 1 is really because there were not, at the time, at the onset of this proposal and a lot of this work, there were no chemicals that were currently labeled to include human health pathogens, right? Fortunately, based on our work and moving forward, we now have at least one. So Sanitate 12 is a PAA-based chemical that is now currently labeled for the reduction of human health pathogens. And so I just took a screenshot, was recently approved this summer. And again, you can see this highlighted section here that Sanitate is available to control Shiga producing E. coli, including O157H7 and Salmonella at these appropriate rates. One of the things I can say is that we do know that there are additional chemical companies, and and others in academia are working with them to see additional label modifications and submissions under EPA. We know of at least two additional variations of this chemical, as well as alternative chemicals that have submitted for EPA label change. And then I'll just say also in the state of Arizona, we've been working with our local pesticide folks at the Arizona Department of Agriculture to specifically look at special local needs permitting. So again, to have options available for industry while we're waiting for these labels to catch up. Specifically on NAGA's protocol, we're looking that the acceptance criteria for these results should demonstrate a minimum of a 3-log reduction. So basically, we're inoculating with this cocktail of bacteria. We're evaluating different rates of application or basically doses of this chemical, looking at a 5-minute contact time, which is what is deemed in that protocol, and then evaluating if we're able to fully see a reduction and more specifically meeting that threshold of 3-log reduction of those test organisms. Just as a reminder, water treatment is not new under the produce safety rule, right? It's always been an option as either a routine operating procedure or corrective measure. But again, as this final rule is the case, growers now have the outcomes of their assessment to drive those decisions. Faith is going to dive a little bit deeper into some alternative pesticide application devices that we do see being used amongst industry members. Here's the ones that we most commonly see being implemented. So on the chemical side, it's either PAA or chlorine dioxide or some chlorine gas or sodium or calcium hypochlorite, so another chlorine derivative. More recently, we've seen the use of UV light. And again, as I said, Faith will be going over some of that data as well. So when we look at the 5 most common kind of disinfectants or sanitizers that we see used in the drinking water and the wastewater world, we've seen this kind of transition for their use in that space and into this agriculture water environment. And so if you look at, I've highlighted the boxes around the effectiveness of these different disinfectants against bacteria. So again, most, if not all, can do a decent job at reducing bacteria, and that's specifically what we're targeting. However, we do have to pay attention to potential regulatory limits on those residuals, and I've got those highlighted there. For those chlorinated compounds, either free or combined chlorine, 4 milligrams per liter is going to be that upper bound or that upper limit. And then for chlorine dioxide, it's going to be 0.8 milligram per liter. We don't see that because there isn't a residual specifically for UV light. And then we do not have a regulatory limit for PAA. Another thing we're often thinking about and chatting with industry about related to the use of some of these chemical sanitizers or disinfectants is that they're not going to kill instantaneously on contact. That rate of inactivation depends on those 5 different factors. And if you think about their implementation in the environment, and more specifically, let's just say at the side of the field, if we're thinking about produce, we have to think about these 5 different factors of the things that we can manipulate and the things that we can't. So obviously we have to think about who we're trying to kill, whether that's a pathogen or an indicator, a bacteria or a virus, for example. The chemical concentration, so in this case, milligrams per liter, or sometimes you'll see us talk about parts per million. The contact time, so the amount of time that chemical comes into contact with the water or that organism that we're trying to kill. The temperature of the water, which we can't really change, right, out in the environment. And then also the pH of the water. Now, we have seen in some circumstances where industry has been able to manipulate pH a little bit, but really on a large scale, it's going to be super challenging. So again, just thinking about that contact time, right, that's the concentration of the chemical times the time. So really thinking about the layout of distribution systems, the application method, and what that looks like in the field. And what Faith's going to jump into after I share some data is what this really looked like in the field and how we can design these treatment systems to be what we believe is efficacious when it actually gets into full implementation. Under objective one, what did we do and how did some of these water treatments perform? We have folks on the contact team spread across the country. So we had 6 different states represented in the data that I'm going to be providing to you today. So we have Arizona, Virginia, Maryland, Georgia, Delaware, and for Florida. For each of these different states, we had research teams collect 2 different water sources. So a water source that we deem to be pretty baseline, pretty normal for that growing region, and then potentially something that might be more challenging. The reason behind the evaluation of most of this data and these water sources is to how variable water quality might be across the country in specific produce growing regions and how that potentially is going to impact the efficacy of these chemistries. So in total, we had 12 agriculture water sources that we were evaluating. We did no pH adjustments with this. And so, again, we're taking these waters as they've been represented, and I'll show you a distribution of what some of that water quality looked like. What we did with those water sources is we sterilized them because we wanted to be able to reduce some of that background bacteria that might with the bacteria that we're inoculating. It's important to note, and I'll mention this again, about how the water quality from these 6 states and these 12 water sources really varied quite dramatically. And some of that water quality was maybe outside the bounds of the protocol that the EPA and FDA developed. And I think that's important. For each of the chemistries, we looked at 2. So we looked at PAA, so peroxyacetic acid, and we also looked at chlorine. For PAA, we looked at a residual of 6 and 10 ppm, and then for chlorine, we looked at 4 and 10 ppm. So really trying to find a mid-range residual and a higher range residual just to have some comparative data to see how they worked. Now, under the water quality criteria and an FDA EPA SOP, they provided some detailed data and information about how to create what's called a synthetic water source. So I just wanted to put this up here so that you guys could see some of the target concentration of these different components in what that synthetic water source was. So again, as a reminder, we weren't creating a synthetic water source. We were just looking at the water sources in those 6 states. But you can see the target goal. If you look at the right-hand side, the target goals for, let's just say for turbidity, would be represented here by the column that says target concentration under the component that says Arizona test depth. And so really the EPA protocol is looking for about 100 NTU. So that's basically the reading that we take for turbidity. And so we would consider is probably the mid-range of what we would see as target for turbidity. Now, what does that actually look like? On the left-hand side would be that test depth that we're adding into that water source. On the right-hand side is some variation and variability in those real water sources that we would have collected. So you can see the broad distribution there. When we dive a bit deeper and look at the variability in the water quality parameters across those 6 states and those 12 water sources, you can see I've got parameters listed across the top here and the average, minimum, and maximum on the left-hand side. Specifically, if you wanted to look at turbidity, which is to the right, you can see the average is about 58 NTU. The maximum for one of those water sources was 472, and the minimum was less than 1. Again, if you look at the pH column, you can see the variability we saw across those water sources there with a minimum of 5.6, an average of 7.62. And then a maximum of 9.6. So pretty alkaline water sources. I think those water sources were some of the ones that we saw in Florida. So the next set of slides I'm going to be showing are going to be basically log reductions. So mean log reductions are each of those cocktails of bacteria. So you'll either see Aztec at the top or you'll see Salmonella at the top. It'll then show the compound that we evaluated. So in this case, we're looking at mean log reductions of Aztec when we evaluated them with chlorine sanitizer at that 5-minute contact time. You can see here we have 4 ppm on the left and 10 ppm on the right. And then the blue boxes are representing 12 degrees which is one of the bounds in the protocol. And then on the right-hand side, you have orange, which is 32 degrees. Now, that red dotted line is going to be your 3 log reduction. So that's going to be what our goal is for the protocol. We want to be able to evaluate. So each of these boxes is box plots representing the range and the variability in those log reductions that we see. So again, as you can see, for mean log reduction for acetic and chlorine at 5 minutes, most of the water samples that we see here are well above that 3 log reduction threshold. If you look at acetic and PAA, again, at that 5-minute contact time related to 6 ppm and then 10 ppm, again, you can see for the most part, we see log reductions above that 3 log reduction threshold, but you can see at that lower temperature, 12 degrees, some of the PAA-based reductions do drop below that 3 log reduction threshold. Again, if we shift a little bit and we look at salmonella, and this is specifically looking at salmonella and chlorine at a 5-minute contact time, evaluating 4 ppm versus 10 ppm residual, you can see at that lower residual of 4 ppm, we see that some variability and again, some dropping below that 3 log reduction for both the 12 degree C as well as the 32 degree C. So some variability there with salmonella. And then again, we see that similar results when we look at PAA, more specifically PAA at 5 minutes, comparing 6 ppm versus 10 ppm. Again, with those cooler temperatures at 12 degrees C kind of dropping below 3. So one of the things that we're doing now with most of this log reduction data as we start to prepare for final publication is try to dive a bit deeper to better understand what are some of those variables that we are evaluating and how potentially they can contribute to better understanding how these chemistries will and will not work and across these different states and water qualities. So one of the ways that we do this is we do an assessment called principal component analysis. So bear with me as I walk through some of this data. Certainly, I'm not an expert, and we work with some amazing folks that have contributed to this presentation. So basically, PCA, or principal component analysis, is a method that allows us to look at a number of different variables in a different way. It helps us dive deeper in exploring the data and potentially group and visualize trends. So if you think about a GIS-based system or similar to latitude and longitude, we're plotting data on multiple different axes that allow us to dive deeper and try to identify what those trends are. As a reminder, for some of the water quality parameters, some of the variables that we're evaluating are those listed on the left-hand side. And if we look at the plot on the right-hand side, the color and how dark the shade of that orange color, kind of reddish color, as well as the size of that dot, talks to us or tells us about the relationship of those parameters with those log reduction values. And so if we look at some of this initial data, we start to see trends related to drivers related to temperature, pH, conductivity, and turbidity. So if we dive a little bit deeper with our principal component analysis and look at these variables that we listed previously, what we start to see are strong negative associations with turbidity. And potentially this makes sense. We've talked about this before and basically seen data related to the influence of turbidity and other organic matter on the ability for some of these chemical sanitizers to work. In addition, we see these positive associations with pH. If we look a little bit deeper at a different dimension of some of this data, we also see some strong positive associations with that conductivity and dissolved oxygen. So again, starting to think about what are some of these variables that are influencing our ability to achieve that 3 log reduction. So basically, if you start to look at this PCA component analysis on the left-hand side, each one of these little labels is represented of a water source and the results associated with that water source. So clusters of those samples indicate that they had similar characteristics. And then what we've done is we've highlighted samples that did not achieve a 3 log reduction in red. And I have a red circle around there. You can see on the bottom right-hand side. So what we're starting to see, at least with STEC and chlorine, if we're evaluating all of the data that we've collected under this objective, we start to see these patterns form, and you start to see the grouping of some of these samples in this lower right-hand corner. If we look at the principal component analysis and try to identify what's influencing those results, what pops up for us is pH and dissolved oxygen as the drivers for some of this data. And so as we go back and think about some of this data, what would be that pH driver? Most of those Florida samples are coming for an extreme alkaline, so a little over 9, so 9.6, I think it was. So potentially in these more alkaline water sources, we're going to have greater challenges with meeting those 3-log reduction. Next, I'm going to dive into some of the additional data from some of our Contact One objective partners, deviating a little bit from looking at bacteria and trying to evaluate, in addition to those Aztec and Salmonella cocktails, thinking about how these agriculture water treatments may perform in other environments as well as on other organisms. So you've heard us on these calls sometimes also start to dive deeper into better understanding of cyclospora, and more specifically, Cyclospora cayennensis. So you've heard from us, and I think Michelle and Callie from the team, we're starting to think a little bit more about the potential root and source of where cyclospora may be popping up in these produce production environments. And water has come up a number of different times. One of the things that's specific to cyclospora is we know that there are different strains, but specifically if you see cayennensis, it came from humans and potentially means that humans are actively shedding these oocysts into the environment. So that is really critical for us to think through as we start to evaluate water as a potential root and cause and source for some of these outbreaks that we're seeing in fresh produce and ways that we might be able to tackle that. So just as a reminder, again, to think about some of the outbreaks that we've seen in recent years, right? So we have the data spread across 2018, 2019, and 2020. So you can see the total laboratory confirmed cases in the thousands. And then if we look at below that, those that have been confirmed associated with produce, you can see those numbers drop pretty dramatically, but still significant. And you can see the mix and the variety of different produce that we've seen associated. So fresh salad mixes, fresh cut vegetables, fresh basil have been potentially implicated in these more recent outbreaks. So some of the challenges related to cyclospora psoriasis and cyclospora outbreaks is there's no real-time genetic subtyping methods that can potentially link disease or illness to a food or environmental sample. So again, extremely challenging for an outbreak investigation, and then extremely challenging for us to also equally be able to evaluate, in this case, treatment with cyclospora. So obviously we've seen a number of cases typically rise during spring and summer, usually during May, June, and July in the United States. The thing that's most challenging, and the thing that was most challenging for this project, is we can't grow it in a laboratory, which makes research on cyclospora, such as agriculture water treatment or strategies for elimination and reduction, extremely challenging. So the data that we're going to be sharing to you today is for some 2 other alternative organisms that we hope better mimic cyclospora in the environment. And additionally, it's been challenging as well because current FDA methods to recover and detect cyclospora in agriculture water was only recently validated, and it's often been questioned about the specificity specifically to cayennensis. So some of the challenges we're starting to face and considerations related to cyclospora in water, we have considerations on the left-hand side, data gaps in the middle, and then research needs on the right-hand side, right? So if we're thinking about potential temperature as a driver for those oocysts to move into a different space to make them ability to infect individuals, we're starting to think about distribution in surface waters and potentially water quality and those impacts on the organism and more specifically its ability to infect individuals, as well as how we can treat them as well. Some of those data gaps, if we start to dive into the literature a bit more, we see variability in die-off rates, but also super challenging to be able to evaluate them because we cannot grow them in the laboratory. So potentially we know it's in these environments and we know that it's in the water in certain locations around the country. But what are those mitigation strategies that we're going to be recommending to industry to put into place to control them? And that's been super challenging. There are lots of research needs related to better understanding of treatment, sources of water quality influence, and potentially those mitigation measures that we might have available to industry. So Callie Neal and the Neal Lab at UND has been doing work on parasite analysis to be able to build our body of knowledge and to better understand water potential mitigation. Because we have challenges with Cyclospora, two alternative organisms that she's been working with are Cryptosporidium parvum, which again is another protozoan parasite, and oocysts. Specifically in her laboratory, these parasites are being treated in a similar manner, right, to that EPA FDA protocol with regards to times and temperatures, as well as those water sources. However, what they have to do because of the protozoan impacts, they're having to use infectivity assays and then molecular methods like qPCR to quantify that inactivation. Additionally, because we know that oocysts are more challenging than bacteria, they're having to treat them with elevated levels and elevated concentrations of some of the chemical sanitizers we've been evaluating. So more specifically for her data set, we've been looking at 50, 100, and 200 parts per million of each of those sanitizers. As you reflect back on the bacterial data I shared previously, in those circumstances, we were looking at residuals of less than 10 ppm. So quite a bit difference, order of magnitude or more difference in some of those residuals that we're having to use to adequately bring down those concentrations of oocysts or Emeria. So some of the key findings coming out of their lab and more specifically thinking about those oocysts. So we have reduction. So in this case, this table is representing the greatest reductions observed in those organisms and those corresponding test parameters. So we've got E. coli, Salmonella, and then Cryptosporidium parvum on the left-hand side. We have the sanitizer concentration in the middle. So again, 10 ppm PAA and 10 ppm chlorine, and then alternatively 200 ppm for crypto. He's held the contact time at 10 minutes and then those variable temperatures. And you can see that obviously we've been able to achieve those log reductions, right? 3.5 for E. coli, 3.4 for Salmonella, and 4.6 for Cryptosporidium. So that's great. However, she is evaluating those higher contact times, so 10 minutes. And you can see that crypto, right, in order to achieve that higher log reduction of 4 points, we are using significantly more residual chlorine or, P compound in this example. Additionally, and this is the last set of data I'll share before I hand it over to Faith, we have another laboratory that's also looking at human norovirus. So again, we focused heavily on bacterial pathogens of concern, but we know that enteric norovirus and enteric viruses are also contributors to foodborne illness across the country and have been associated with infections really with untreated recreational waters in the U.S. And so if we're considered risks related to untreated surface waters and we're potentially using some of these waters to irrigate produce, potentially there might be additional transfer mechanisms at play that may play a role in human norovirus outbreak. So here's an example of some of the water sources that were being evaluated. These are in Florida. These are photos courtesy of Dr. Daniluk, and specifically looking at some of these chemical-based sanitizers for norovirus reduction. For viral analysis, and more specifically for this assay, we're looking at something called PFUs or platforming units. So on the right-hand side, two Petri plates. Each of those clear zones represents where there was a virus present that basically ate away or destroyed the vectors. We count up all of those clear zones, and basically that tells us the concentration of the virus or that organism that was present in that water sample. So here's some of that initial data that's coming out of the laboratory, specifically looking at another virus that mimics human norovirus, the Tulane virus. So on the left-hand side, we see the E. coli log reduction over residual. So we have log reduction on the left-hand side, and then you have free available chlorine along the bottom. The blue bars represent 5 minutes, and the orange bars represent 10 minutes. And you can see the E. coli on the left-hand side. Pretty quickly, we're able to see reductions in that E. coli. But when we compare that on the right-hand side to the virus, it's going to take a significantly higher amount of free available chlorine to see similar log reductions there. So again, thinking through how agricultural water treatment potentially can be very good at tackling some of these bacterial pathogens. It's going to be much more challenging when we're starting to think about viruses, and in this case, human norovirus, as well as the protozoan parasites, thinking about cyclospora. All right. So what does this data tell us? So most of the water treatment chemistries can work, as you saw with that data, but Salmonella certainly is going to be more challenging than S-Tech, and then Protozoa will be especially challenging, as I just said. As we start to dive into what drives efficacy and into some of these contributing factors, we've identified that pH, dissolved oxygen, and turbidity are going to be those main drivers of efficacy. Again, those lower contact times and those cooler temperatures are going to be more challenging. So potentially that might encourage some variable treatment programs based on seasonality. And so what are we doing in the meantime as we kind of work through what this rule implementation might look like, and we work through what mitigations might be achievable by industry? We're asking folks to get out there and try. So basically sampling and evaluation of your mitigation strategy and your treatment. Pre and post sampling coupled with that monitoring are going to be your best bet at achieving those target log reductions. And again, Faith is going to drive that point home with some of her information. Again, it can be successful. And so it's not all doom and gloom, but you have to know your water source and identify what typical seasonal trends versus what are not typical, and really how your system is going to react to some changes in the environment. So lastly, in accordance to the rule, we're thinking through what we're telling growers and what implementation will actually look like, what inspectional approach might be. And we're having those conversations with inspectors right now. So obviously treating according to the label language. And as we said, we only have one labeled chemistry. So what do you do in the meantime? So if water treatment according to the label, and you have water test results post-treatment with really low levels or potentially non-detective that generic E. coli or other relevant indicator organism, and you're meeting the previously established statistical threshold values or geometric means established by FDA in 2015, potentially water testing could be used to verify your treatment efficacy or justify their action. So basically, arming growers with the ability to collect their own data to prove the efficacy and prove their mitigation strategy. However, as Faith is going to go ahead and start off, that's going to be challenging as well. And so there are some strategies when you're getting into the field. So I'll go ahead and end there. There's my contact information. I know we're going to have time for additional questions as well. I will let you take it away, Faith.
Okay, everyone. I'm really happy to join you today and talk with you a little bit about some of the emerging water treatment technologies. And then we'll wrap up with some actual field implementation, just so you can start to get your eyes on what we see as far as variability and things along those lines when we scale these systems up from bench scale all the way up to 500 to 600 gallons per minute in field application. My name's Faith Critzer. I'm a professor at the University of Georgia and really love working with the fresh fruit and vegetable industry. So I think that she has given us a really good primer on different ways we can look at treating agricultural water. The one that I'm going to focus on today is UV light. It falls within this realm of when we think about agricultural water treatment, especially and honestly, any sort of treatment we apply to water. It is considered an EPA registered antimicrobial device, and these devices are really handled slightly differently under the EPA regs, and that the manufacturer of these devices has to register. They are never going to have necessarily a label per se, though, and essentially you'll rely upon that supplier to help with the supporting documentation for how that treatment has efficacy within that application. You can tell that there's other things listed on here, and this is by no means all encompassing, but definitely ozone falls under this category. We can also see filtration. And even when it comes down to it, you can even find devices that are generating chlorine and things along those lines that people are moving to that fall under this antimicrobial device category. So when it comes to challenges associated with this, What I can say from the viewpoint of a UV light sort of installation, there's been really limited movement on sanitizers that have been registered with the EPA for pre-harvest water treatment for foodborne pathogens. Clearly, Channah's given us an update that we have one labeled product that is approved and a few other moving in that direction, but we really weren't seeing a ton of movement, and that's not unexpected considering how new this is. We know that it's for all of these different suppliers. When you look at the grand scheme of things across water treatment in general, the agriculture water treatment sector is a really small segment of that industry. And so it's really hard to make a business argument for many in that industry to start supporting the ag sector. We also know that there's a little bit of lacking of clarity around what efficacy must be demonstrated to be deemed effective for devices. We would assume that it would at least be the 3 log reduction we're holding our pesticide products to. But is there going to be other information required for these devices, which I think will be really helpful to outline it from the regulatory perspective in the future? So let's do a little bit of a primer on UV light, and then we'll show some data with actual efficacy and looking at different treatment options within surface water. So UV light is a spectrum that is actually quite wide, just after visible light within our electromagnetic spectrum. Typically, if we're talking about germicidal UV bulbs, we're around the 254 nanometer range, but know that sometimes you'll see variability there. For instance, if I want to generate more ozone, I go more towards the 180 wavelength. And most commonly, though, what we're seeing is 254 nanometers within that UVC range for germicidal activity. And this has been the case for decades now. We know that by default, and Channah already mentioned some of the physical chemical parameters that can drive efficacy of different treatments within the pesticide products category. But UV light is also going to be prone to some of these same physical chemical parameters. For instance, since its mode of action is that it actually has to penetrate the bacteria so that it can start basically causing cross-linking within the DNA, ultimately causing death to that organism, you're going to need to basically get light onto that organism. Clearly, things like turbidity are going to negatively impact this activity. For the Arizona, we were targeting for those water kind of makeup water, I guess that we were saying for the bench scale. For the EPA sort of testing, we're somewhere right in here in that 100 NTU. So that kind of gives you an idea about what that looks like. And from a visual perspective, I would say that turbidity, when it comes to treatment of agricultural water, is going to be highly variable. Many times when things start to get drier, we're going to see turbidity potentially increase as we're pulling from closer and closer to that sediment layer on the bottom. Clearly, things like runoff and things along those lines can also impact that. And many times that's coming at you. If we're talking about a river or something like that upstream, you may not always be, it's not always directly associated with rainfall occurring right at that time. We know with UV lights, they're widely used for water treatment as well as other applications for trying to keep microorganisms at bay. They lose activity over time, but most are going to have a 10,000 hour life. And I would say, with my experience in handling these systems in the field setting, you're probably going to do something to break the bulb or the ballast before that life span is reached. We also know that it is imperative to clean the quartz glass sleeve during operation to keep growth from impacting transmission, because you will get algae and other biofilms forming on that, and that will directly impair treatment when the system's on and operating. We know that when we see these systems installed, they're typically in built facilities when it comes to food processing, or they're used for municipal water. Occasionally, you'll see them the home scale, handling somewhere around like 10 to 7 gallons per minute for people who are using groundwater and things along those lines, or spring water. But in general, we have not had the uptake by the ag industry in the past, and the industry hasn't really moved yet to start filling what needs that sector may have. As you can see here, we have a few different installations. So the installation that I think is the most helpful for you to look at is the one from Channah Rock here on your screen, which is showing it clearly installed in the field. That UV light for each one of those lights aligns to one bulb within this system, typically for treating higher volumes of water. we're either going to have to split the water into single streams where we can put one bulb per stream and then bring them all back together, or we will have to treat with multiple lights immersed within that water stream. And that's what you're seeing here. You can see on the inside, we have these from municipal water treatments. Again, with the one on the bottom showing basically the wiper blade that comes across, and these systems, they can have a lot of bells and whistles to them. But inevitably, you will need to have either automated or self-run cleaning systems within these systems so that you can keep them clean and operational. Because it is really a bear to break the system down and try and clean these by hand. You're going to need that to occur far more frequently. You can imagine why we say that not been very friendly to the field setting. Clearly, you're going to have electricity, and I know a lot of growers are already dealing with that because they're pumping. But again, you're going to have electricity, again, additional to that, you're going to have to supply out to the field. And these are not really going to be very conducive to moving around consistently, right? So it's going to be like you put it in place, you set it, you get it up and operating, and you leave it throughout that duration that you're going to need it. As far as the EV light industry, it is growing. So I think there is room for accommodating that sector. And what I've seen with any business is that they will make room if they understand that there is a market there for them. Right now, they're at 365.5 million sales in 2022. It's estimated to grow to about a $1.2 million business in the next 10 years. And primarily that growth is occurring in North America as well as Europe. And most of that is occurring within water, but also definitely the pandemic did drive more sales towards air purification as people are investigating that as a remediation step. When it comes to thinking about UV light, a lot of the advantages is that it can be combined with other disinfectants. And so you can get additional dialing in what you're treating for and what you're targeting. Channah showed it on her graph looking at the 5 different common types of water treatment. UV light does have that benefit in that you can get a really good activity against protozoan parasites. So maybe if you had that concern, you could treat in that regard for protozoan and parasite, and maybe you would rely upon another treatment for something else, another target. It's low cost associated with system use. However, that's once you get that initial investment paid off. And there's no downstream activity to interact with other compounds. Sometimes this is a good thing, sometimes this is a negative thing. So if I was, let's say, injecting a fertilizer and I had chlorine in my line, I may get cross reactivity with that fertilizer. I may see my chlorine bottom out and I not have any residual at the end. Something like UV light is only getting treated in the duration while it's exposed to that light. So if you're injecting afterwards, you're not going to get any cross reactivity with that compound. Sometimes this is a negative though. So I'll say you could straddle it over into the disadvantage category, which is what I've done. As the last bullet point in disadvantage, there's no downstream activity. So if we're trying to prevent whatever makes it pass is making it past, we are not getting whatever benefit we may be getting from having that sanitizer within the water. We are not essentially sanitizing our line with this treatment. So we will not get that sort of protection. So you may want to think about that, especially as we start up or end on the season before we put things away. Other disadvantages are there's that high initial investment cost. It is hard to maintain in a field environment, and there are going to be high maintenance costs associated with it. And I would say this is not something specific to UV light. We would see it in any sort of device like a ozonation unit or anything along those lines. Water turbidity is going to limit effectiveness, but we're going to have some data here to speak to ways that we can deal with that. So let's look at some efficacy in surface water treatment. This is a unit, and this is a great example of a split unit where this unit was only handling about 60 gallons per minute, but essentially you stack these. So this is what this would look like if you're trying to get around having multiple bowls within one single chamber. From an efficacy standpoint, they all work very well and are designed to work well and based on the parameters they give you. So this is work from Jones et al. Looking at efficacy in surface water against bacterial foodborne pathogens. This work was not done in the field setting, but it was done in surface water. Ultimately, they targeted Shiga toxigenic E. coli, Salmonella, and Listeria monocytogenes in this work. And they applied a dose of 14.2 millijoules per centimeter squared. That is our dose that accommodates both how much energy we're applying, compounded by the amount of time that water flow is exposed to that UV light. So that is how we would talk about something equivalent to a dosage for an antimicrobial product. For our water sources here, they have a not surface water source. This is just a microbiological media that has very little within it. A creek and a pond here. You can see that on average, as our turbidity goes up, we can see that we have a little bit of a harder time in trying to actually compound and counteract that effect of that turbidity as far as treatment goes. What they saw, this is their data set from this study. And so we can see each of those water sources. And remember, with our pond, we're seeing higher turbidity. And I think that's reflected here, as they are all very similar as far as pH goes and things along those lines. So you can see here, this is just to orient you, this is that microbiological media in our first column, our creek in the middle, and then our pond secondarily. And we have broken this out by organism. And this is log reduction. So the higher the bar, the better we are. And this was in CFU per liter. And so we're looking here, when it comes to E. coli and 157H7, we didn't really see a difference there. And Ecvacine had very similar results across the board. However, I would say that it's most pronounced for Listeria, which is a slightly different type of microorganism versus E. coli and Salmonella. They have slightly different kind of framework that their cell membrane is built around. And we did see more of an impact from that turbidity within Listeria monocytogenes, that we saw a little bit less activity, but still showing fairly good activity across the board here, achieving a much greater than 3 log, somewhere around a 9 log to a 7 log reduction in all cases here. So definitely showing promise as far as we could get an activation within these systems. We also were looking at some work from Rohan Tidkar's lab, who is also part of the Contact grant. This preceded Contact, but essentially what they did in that work is they were working with an attenuated E. coli 157 and looking at an activation with varying turbidity and UV light. You can see in the next to the last column, they have what they call the average D value in UV energy. So that's showing that as I increase my turbidity, essentially, I also have to increase the dosage of UV light. And I do this by slowing down the flow of water. So we can see that in that 500 NTU sample, the highest turbidity sample, we had 114 seconds exposure time. And that is what is driving up that D value for that next to last column. And also see that they've gone through and averaged out the time for a 5 log reduction for these target organisms. So we can tell that definitely as we go, especially above 100 NTU, we can see a significant increase in the amount of time that we would need to take to treat this water. Also part of the same study from Rohan's lab is that they looked at how well sand filtration worked to decrease turbidity within this water source, since that was one of the primary drivers impacting efficacy. What you can see here is on the line graphs on this side, I think it shows a really nice picture. In the light blue lines, we have before filtration and the particle sizes of the various particulate that was in that surface water. We can tell that by going through a filtration step, which is our dark blue lines there in panel C, we can have a really good reduction in the percentage of that incredibly large particulate, somewhere above 5,000 nanometers in length. And that's going to really help us try and reduce the amount of essentially shadowing and blocking of that light that may prohibit activity and actually reaching some of our microorganisms that we're interested in targeting. Definitely, we can see that you can tell that other than just the particulate size, you can also tell that the sand filter is definitely impacting turbidity. So even though I'm not expecting you to have a particle size analyzer, you can definitely look at how this does drive down turbidity where we were before the sand filtration above 500 NTU. After sand filtration, we were pretty consistently getting it somewhere between 200 and 250. We also have work from LSU and a shoot out of Kari's lab looking at generic E. coli and surface water sources, again, taken from production regions that was recently published in 2020. Within these, again, we're looking at varying quality of water. So they looked at well water, and then essentially what they did is they mixed well and pond water together to get the middle two categories that were designed basically to differ by both turbidity as well as the pH slightly. We can tell that our well water is a little bit more alkaline, but our pond water is not far behind it at pH of 7. So right around neutral to slightly alkaline. We can see in here that we have relatively low turbidity across the board. So this is more in the range of, as you can see, 10 to 20. So very lightly cloudy, I would say. It's recognizable, but nothing upwards of 100. For our reduction, what we can see here in this other table is looking at the reduction of generic E. coli in those 4 water sources using UV light. They separated each column by dose, so we can see how much reduction we get as we increase that dosage. And I would say across the board, we do see that even slight difference in turbidity is making a difference in our overall log reduction at our lowest dosage. And many times, I would say with the flow rates that we're seeing, we are somewhere in that 20 to 30 millijoules per centimeter square range, which is that first column there. But even with that being said, we were still able to achieve a 3 log reduction in that kind of highest turbidity scenario. We can also see that as we go across, as we increase that dosage, we can raise that inactivation rate. So we can get greater inactivation if we were targeting that. Again, this speaks to some of the issues when it comes to turbidity. We do have a lot of particulates within the surface water. And so I would say that while I showed you some data with sand filtration, I would say any filtration source is going to be an added bonus. And you should look at doing that prior to UV light treatment because you're going to counteract some of these things that may kick up. I know that several of you are in have very high water quality you're pulling from. It may not be turbid at all, but in this example, we are seeing differences as few as like 10 to 20 NTUs was making an impact there as far as the log reductions we were able to achieve. So from some of the takeaways we can see is that the efficacy for bacterial foodborne pathogens has been demonstrated in both the lab and that field setting. We're going to show you a little bit more spanning into larger field operations. We can regularly achieve a greater than 3 log inactivation of indicator organisms. Turbidity is one of the primary factors, and as far as efficacy goes, and what we've really linked to giving us largest impact to overall efficacy within that system. And we know that's also difficult. As a grower, you're going to be using and pulling in whatever water you have available. It's not as if you can say, no, I want the less turbid water. So just getting a feel for what's that range in turbidity, what might these systems look like? And I would say it would be a pretty easy no-brainer to always say you're going to need to have a filtration step involved, like standard disc filter. So let's take a little bit more time to actually look at implementation. And this is not just with UV light. This is with a lot of our compounds. This is work that's part of Contact looking at chlorine mapping on farm. This work was conducted by Rowan Rod within my lab. And in this operation, we were working with a grower that's growing on 100 acres. They have 4 25-acre zones that they're irrigating into. And they know that they have groundwater that is under the influence of surface water. So they have been treating their water for quite some time, honestly, to deal with non-food safety related organisms like iron-producing bacteria. However, they were more than happy to partner with us and have us come in and look at their system. They were using chlorine gas, which is something we haven't really emphasized as much. We do have quite a bit of chlorine gas. It is still providing free chlorine within those systems that has slightly different OSHA and I would say regulatory concerns that should be considered before implementation. Within the system, they were typically irrigating. Again, we would just come to the farm, make a visit, and monitor their free chlorine within whatever zone they are irrigating in. And out at those zones, we were looking at rates of 300 to 600 gallons per minute based upon the day that we were coming. The dosing target that they had were 3 parts per million free chlorine. And you can see some of those parameters that Channah was emphasizing here, and that we had conductivity. The conductivity was highest when they weren't treating, and the iron forming bacteria were highest. So that definitely skewed that data. But turbidity, it was ranging from 5 to 68 MTUs, which is quite high for groundwater, very indicative of it being under the influence of surface water. The COD was somewhere around 7 to 32, 342, so quite a large range there. And then they also had pH ranging from 7.5 to 6.5. Generally speaking, when this water was treated, we did not recover any E. coli per 100 milliliters. And for the coliforms, we were somewhere around 0 to 10 MPN per 100 milliliters. That's not log transform data. Those are just exact counts. Within this system, we anchored this data to a few words, and I just want to make sure we're all on the same page. So we were monitoring at the point of injection. So right there at the pump, really high volume of water coming through there right when that chlorine gas was being injected. We also have data points that are reflective of header. And so this is like the header at that zone where you had essentially the closest to that point of injection. And then we had what we called our distal point. So it was at the last point of contact within that zone for this operation. What we did is we simply went in addition to doing the generic E. coli and coliforms, we also mapped out free chlorine throughout this system. This is just those 3 locations. We collapsed all zones together because we did not see a difference between them. You could potentially see differences depending upon how far apart your zones are within your irrigation setup. Within this, I think one of the things that surprises people the most is that how low at the point of injection our reading was. The takeaway there is that although that may be the most convenient point to sample from, you're not going to get a very good reflection of what the actual concentration is going out at the field level. Because you haven't had adequate time for mixing, the product's just getting injected in there. And I would feel really confident saying this would be the case even in a liquid injection system. As we move towards the header, the biggest thing about the header is we have a lot of variability within that system, and it's not quite as evident within that distal, the very end of that irrigation line. I want to zoom in here just so we can take a little bit closer look. These are same data points. I just removed the outliers and pulled us in from 3 to 0. What we see within this data set is that you get the highest concentration at the header. That makes sense, right? Because that is where we've had adequate mixing has taken place is the goal. And then essentially we have, unless it's reacted and it's been fully exhausted, we should expect to see the highest concentration there. We notice that we do see a drop in that distal sampling point, and that also makes sense, right? Because the free chlorine is going on to react with whatever compounds coming in contact with, and so we should expect for that to be exhausted at that point in time. I'm going to now show a little bit of work that we did with the Washington State. We try and anchor these into kind of all these factors that we're seeing. Within this study, we were looking at PAA injection, chlorine injection through calcium hypochlorite, as well as UV light. This is out at a field scale. In general, we were trying to target for our compounds 5 parts per million. For UV light is 30 millijoules per centimeter squared. Our contact time was 30 seconds at our point of sampling. And you can tell that even we're dealing with slightly alkaline water, 8.6 to 8.8. For our chlorine treatment, PAA injection alone brought that down to 7.5. And we were dealing with turbidity somewhere between 2 and 16 and a water temperature of 17 to 20 degrees Celsius. For these concentrations, this is really looking at our indicator organisms and generic E. coli and coliforms, and looking at how stable was the system once we got it up and running. Essentially, at this point, once we ran that system for 5, 15, 30, and 45 and 60 minutes, how much variability do we see as far as microbial reduction? The data we have in here are actual populations of long transformed populations of coliforms. We did not have a very high concentration of E. coli, and our 0 time point represents no treatment. And afterwards, so you can see we're about 1,000 or greater, and that we're 3 logs for our coliforms. And as we move through, we can see that we consistently obtained across the board with all 3 treatment types, UV light, chlorine, and PAA, a 3-log inactivation of that indicator. And it was fairly consistent over time. So we didn't see a lot of dips and things along those lines as far as efficacy goes within that system. And at the same time, we were always bouncing around somewhere typically between 2 to 7 parts per million, even in these setups for our injection. This is some data from Michelle Danieluk in similar data set where we're looking at actual application in the field. You can see here they were targeting 2 different concentrations for chlorine versus PAA and a wide range of water pH. Their contact time was roughly the same, but their turbidity had a whole lot greater separation from water source to water source. Whereas we were only working in Washington State with 1 water source, they were pulling from 8 different ponds and visiting them 3 separate times to collect this data. Within their data, we have first chlorine. You're going to see a series of red lines or orange lines and green lines. The orange lines are 3 different trips out in the untreated water concentration of coliforms. So we're somewhere around 3 to 5 for these visits in these 8 different ponds. You can see that the green lines represent the sodium hypochlorite treatment, so the treated water and the reductions that we saw here. We can see that ultimately sometimes things do not go by the playbook, right? She was also looking at a trajectory over time, so we would expect in pond 6 these data points to all be down closer to the other 2 reps, but clearly there's something else going on that day that was interfering with this treatment. And the pond 7 and 8 also have asterisks there. Those asterisks represent salmonella detects within 150 milliliters of water within this treated water system. So that's showing that we are having salmonella naturally present in this pond break through to that treated water sample. When looking at PAA within the same pond sets, we can see that PAA is slightly more variable between replicates in some instances. We can also, though, tell that we did not have the same breakthrough events in salmonella that we had identified in our chlorine treatments. So again, trying to get at, and part of the work that Channah's been doing is really trying to figure out with other parts of our modeling team, what is causing this variability and how would people account for it over time. But I would say expect, if you're looking at doing this on farm, expect a lot of variability, and that's going to increase maybe the number of samples you need to pull to get these systems locked in. So to try and bring it home, I think that this data set, as well as others that we've shown, really speaks to the fact that validation is going to be key to implementation. It's going to be specific to a water source and a site, and we cannot necessarily translate from one location to another very easily. This is not uncommon to what we see in post-harvest water uses and other things, though. So I would say that while it's a bit disheartening, it's not unexpected. Pre-harvest water treatment will require significant allied industry support and partnership. I would say that there's good news there. Many of you are part of that allied industry, and we know that we have options that work in a field setting for our target foodborne pathogens. What players ultimately are going to invest in this segment, I think it's going to be a real big question for the industry, because you are going to need those good partners on the treatment side. And then other constraints around water availability are likely going to continue to push innovation in the sector, especially in the ag. There are a few of my references from some of those studies that I showed. And then thank you very much again for letting me come in and tell you a little bit about UV light, as well as some of the great field work we and others have been doing, all trying to help support the industry.
And thank you all for joining us.